Okay. Hi, my name is Saikrishna from Microsoft. I'm going to be talking about using BTRFS, or as some people call it, BTRFS on Sonic for a compact and resilient image. So the previous talk talked about reducing the features of Sonic, changing how the Sonic image runtime is to get a smaller Sonic image size. This is looking at it from another angle. Can we make use of the disk more efficiently while still keeping all the current features of Sonic as it is today? All right, so in case you don't know, when you install a Sonic image, what does it look like on disk? So this is from a output from a sample device. In this case, it's using the MMC storage. It has 3 partitions. In this case, Sonic is installed on MMC BLK0P1, the first partition. Second one might be ONI. Third one might be some filler partition. On the disk itself, everything that is on the disk ends in the /host directory. And there will be one folder for the bootloader, in this case, grub, and a image directory that has all of the files for the Sonic image, that particular image version. Now, the folders within that directory we're going to focus on today is the fs.squash.fs, which is the base file system that system D is running, and Docker is running on. It's currently a squash.fs compressed file system, and then the Docker folder, which is where all of the Docker containers live, basically the data directory for Docker. So I took a boot Broadcom image from master branch. I think this was as of a couple of weeks ago, and after installing it on a device, the disk usage was about 2.1 gigabytes. And looking at what got installed, there were about 24,600 files and 6,300 directories, which is a lot of directories. But also keep in mind, this is also including all of the Docker containers, so all of the files in there, the metadata, and so on that is present. And because of the image structure that we have, the files might be duplicated between the base and the Docker. So for example, SWSS common is installed on both the host and in the containers. There's going to be 2 copies there. That's going to be taking up space. And in some cases, within the different Docker containers themselves, there might be duplicated files if the same package is installed in 2 different places. So yeah, as mentioned, there's duplicated files and contents. If we try to do some magic with OverlayFS to try to get rid of that duplication, we might run into restrictions with mounting OverlayFS on top of OverlayFS. The kernel doesn't like that. In addition, with the number of files that we are writing, the individual files, individual directories, some of the hardware that Sonic runs on today, it might not have like best-in-class SSDs, because typically that is mainly for servers. Network switches don't usually have a pressing need for that. So over time, there's a potential for corruption in some subset of files. Maybe something got messed up when trying to write the file to the SSD, or there was some silent bit rot that happened. So there's potential for corruption that we won't know until something goes wrong at runtime. And as we go into future Sonic releases, there's going to be more and more features. That's going to take up more and more space. So what's the solution? We redesigned the layout of how we store the Sonic image on disk. So where does that get us? So what we can do is store everything in a single loopback image, which is to say a single file. So this file will in itself be a file system that can then be mounted as if it were like a regular disk. Our init.trimfs will mount it as the root file system, and then we're going to create the host directory in there, and then that's going to contain like the base image, the release files, as well as the Docker containers. It doesn't require manual changes to devices. So what I mean by this is that this approach can then work with just doing the usual Sonic installer install commands and then reboot into that. We don't need to repartition the disk or anything like that to make this feasible. And the file system of choice that I'm choosing here is BTRFS. Primary reason being it's a sort of a newer file system that supports more features, and I'm familiar with it as well. So what is BTRFS? So BTRFS is a copy on write file system, meaning if you make a change to some file, the file system will copy the file somewhere else on disk, and then change the pointers to that file in the directories to point to that new copy. So it doesn't modify what's already been written in place. It creates a copy of it. The advantage of that is that any changes you make are hopefully atomic. You don't get like a mix and match of what was there before and what's there now. It is currently in use by Facebook, and it is on the default file system of Fedora and OpenSUSE, as well as Synology NAS. It supports data and metadata checksums. So right now, ext4, which is what we use, only supports, I believe, metadata checksums. BTRFS supports data and metadata, meaning every time you write a file onto the file system, it will write alongside with a checksum for each block of data. When you read a file, it reads the checksum, make sure it's correct. If it's not correct, it will either try to repair it, or if it can't repair it, raise a big alert saying, hey, this file is corrupted. It supports transparent compression, meaning that what you're writing to disk, what might be in there, might be compressed on disk. So let's say if you're writing 4 kilobytes, or let's take 4 megabytes of data, it might only be that gets compressed and only 1 megabyte gets written to disk. It supports block level deduplication. What this means is that if you have the same thing present in multiple files, because like even in binaries and shared libraries, there might be code or data that pretty much looks the same in terms of instructions in multiple files. It will reuse, it will only have one copy of that shared data, and it will sort of reuse that data for both files. So with this, in the case of having duplicate data between like the host and one of the containers, or even different container layers, those files can then be effectively shared on the disk. There's no cost of duplicate files here. And finally, it supports subvolumes, which is the easiest explanation is like a subpartition that you can make. You can make any number of subpartitions, subvolumes in BTRFS. There are some requirements, though. It requires that the disk does atomic block reads and writes, and fully flush contents the disk when the file system asks it to. These are typically already done, already present. In the few cases that the file or disk in question doesn't appear to be doing this, there are detection mechanisms in the file system itself. And if it sees that, it will flag it. There will be kernel messages about this. The other catch is there might be a noticeable issue of write amplification. If you're writing small files repeatedly, because of the copy on write nature of the file system, it might be that it writes more data to disk than what you yourself wrote. This is partially mitigated with caching and grouping of writes at the file system level, like within the kernel, as well as potentially within the drive firmware. But it is noted that this file system isn't meant for databases or virtual machines, which fortunately Sonic isn't using today. So what this looks like is that we have our disk /dev/sda3. So this is like some partition on the actual physical disk. On top of that, in the /host directory that we were looking at, within, in this case, image master directory, there will be a single file called, say, filesystem.img. This will look like a regular file. This takes place of the Docker directory and the fs.squashfs files. It has both of them in it. This can get mounted as a file system, and then that will become the root directory, essentially. So that green layer is what will become root when you log into Sonic. That green layer is basically sitting on top of a single file. Basically, it's reading contents of that file, interpreting it as a file system. And then the overlay is all of the overlay mounts that Docker creates for its containers. So with the solution, we reduce the boot time mount complexity. So right now at boot time, we are creating overlay mounts for the base file system, the base image. We won't need to do that. We won't need to create a read-write directory. We won't need to do a bind mount of var-lib docker, which we're doing today. It will just be a single mount command, mounting that file system.img file. It reduces the image installation complexity because now when we are installing an image, there's just going to be like maybe a few tens of files being installed, which is going to be more performant with ext4 because it will be able to write to disk at higher speeds. It does slightly increase the build time packaging complexity. While there's no need to create a container tarball, the dockerfs.tar.gz that some of you may have seen, there's some added complexity in making a loopback image, mounting it, installing it into there, and then running the deduplication to reduce the disk space that is used. There are some drawbacks with this approach. The loopback image, because it's just a regular file sitting on the drive, how much space you have in the loopback image, which is to say how much space you have within the Sonic installation, is bounded by the size of that file. So if your loopback file is like 1.5 gigs or 2 gigs, then you can only write 2 gigs of data in the Sonic installation. The advantage of that is you won't accidentally fill up the entire disk in case some process goes rogue and writes a bunch of data to disk. Downside is you won't have the full disk space available to you. You can do bind mounts of the /host directory, which will have full disk space access if you do need that more space. Because this is a sort of a newer file system, there are new features being added, which in some cases might make it difficult or impossible to mount on older kernels or file systems. There are ways to mitigate that by setting flags or disabling flags the new file system creation tool uses. The write amplification issue mentioned earlier is one of the drawbacks here. There may be higher CPU usage because of the added checksumming that is there, and read-write latency because of higher checksumming and copy-on-write file system. And the current Sonic image installation code may need changes if you are doing something like mounting the new file system from the new image for firmware updates like BIOS, CPLD updates, or something like that. So what do we get out of this? So this is basically a high-level summary of the steps I did for the purposes of this experiment. I took an existing master branch image, extracted it, converted it to use a BTRFS file system in the loopback image, and then repackaged it, installed that, and then with the current image that we have, That took up the image file size itself was about 820 megabytes. With the BTRFS loopback, it's 760 megabytes. Not that much of a drop, but that is to be somewhat expected since even the current image is somewhat compressed. The disk usage went from 2.1 gigabytes to 1.6 gigabytes on disk. However, this is before FS trim was run, which is basically getting rid of unused blocks. It's telling the SSD that it can use those blocks. Once that is run, it comes down to about 990 megabytes on disk. Boot up time remained about the same, 1 minute in both cases. System load, the numbers were captured after, I think, like 1 hour or so, and there is a slight increase. But I noticed that the numbers were higher even before that 1 hour mark. So my expectation is that there will be a slight increase. The degree of that increase might be variable. So with BTRFS, we can get a bunch more features. Because of sub volumes, we can do like snapshots. Let's say you're making some change to the sonic base image. You can take a snapshot now, make your changes. If something doesn't work out, you can go back to that snapshot. You could do some sort of RAID installation if you have multiple storage devices present on that particular hardware. You could do frequent checks to see if there's any silent bit drop or anything happening there, what BTRFS calls scrubs. And there could theoretically be some sort of future layout where we have multiple images stored in a single loopback image. The idea being that only the changes between the images are added to that loopback image. That will be much smaller in space. So yeah, thank you for the presentation.
Yeah, I try to understand like what's the real benefit, because from your table you presented, it looks like only 500, like a mega, the space will be saved, right? But on the end, you also mentioned like say that means that from the upgrade image point of view, you only add the delta on top of it.
So the 500 megabyte part, so that is with so when the image is installed, the disk space that is used is 500 megabytes smaller, which I think if I recheck the numbers, is almost, actually, no, I take that back. It's almost 1 gigabyte smaller after you run FS trim.
Okay.
Which is almost 50% of the space given back to you. The delta for upgrading images, that's a theoretical future potential. That's not considered in this design because that would mean more changes. It would get slightly messier.
Okay, so the takeaway basically is that half of the disk will be used for storing the image.
The disk usage drops in half, so it goes from 2.1 gigabytes down to about a gigabyte.
About a gigabyte, yeah, gotcha.
So yeah, small storage platforms, great use case.
Okay, thanks.
Okay, thank you.